Okay, chapter 4 of chemistry. Now, I told you guys you only had to start reading on page 105. Pages 97 to 104 in chapter 4 have some information that explains why this makes sense. If your mind enjoys that whole explanation, feel free to read it. But if you start to read and it just confuses you, don't worry about reading it. That's just lots of information. So, going through your note sheet. We talked about the Bohr model, but we also said that's not fully correct. That's what we talked about in chapter 3. The current atomic model that we use is called the quantum, Q-U-A-N-T-U-M, quantum mechanical model. Quantum mechanical model is the current model of the atom. We say current because it's changed before, could change again. Okay, so quanta is a packet of specific energy. It's a little packet of energy. That's what a quanta is. This quantum mechanical model replaces orbits, hi Dougie, with orbitals. Okay, you gotta go that way. Go. Sorry, we don't get a ruby today, we get a boomer. Okay, we replace those just orbits in the Bohr model with now orbitals. And you can see in your book, they'll show you pictures of the what they think the orbitals look like. They can also be called electron clouds. Electrons are somewhere in the orbital, but they're not necessarily a specific distance. So in the Bohr model, you had your protons and neutrons, and then you had electrons, and they would have always, each orbital was exactly a certain amount from the center. Each orbit. But now with these orbitals, they're not going to be exactly a certain distance from the nucleus. Okay. And so you've heard quantum mechanics probably before. That's kind of what some of this is. We're not going to go in depth into it. We're just kind of getting a basic understanding. Okay, then we talk about orbitals. The s orbital is a sphere. The p orbital is a dumbbell. The d, there's 5 possible. They're available at the 3rd energy level. And that's why you guys have this way of learning to write them. We talked about this in class, how to write the orbitals, where the electrons are at. You just follow the arrows and do the next one, filling until you get enough electrons for how many ever electrons that element has. Remember, we find the number of electrons by looking at the atomic number of the element. So if we have lithium, its atomic number would be what I didn't bring my book. Hold on, let me grab a periodic table. I'm not gonna, hold on.
Hello!
Sorry, that was easier than pausing. Okay, so lithium has an atomic number of 3, and then it has a mass of 7. So remember that little number up in the corner, the left-hand corner is the atomic number. That's its number of electrons. So if we're going to do lithium, you would start with 1s. S can have 2, so you'd have 1s2. Then you would go to 2s. 2s can have 2, but I only need 1 because that 2 and that 1 gives me 3 electrons. And that's all I need is those 3 electrons. Okay. So I had you write on there, S can hold 2, P can hold 6, D can hold 10, F can hold 14. You can look in your book. You will be doing some practice with writing them. And I showed you that there's kind of a shorthand way. Your book will talk about that. If you can't understand the shorthand way, just do it the longhand way. It's not like you're going to be writing a lot of these. But you just keep writing them. Keep following the arrows until you get them. Do some from your book. Look at them in your book. It will make sense, hopefully. If not, let me know. I can help you. I'm more than happy to sit down and help you work through it. Wave-particle duality. Wave-particle duality is the concept that light, as well as many subatomic particles, have the properties of both particles and waves. So, wave-particle duality is the concept that light, as well as many subatomic particles, have the properties of both particles and waves. So it can be a little packet or it can be a wave. That's the duality. Okay. Off-ball principle. Electrons fill orbitals starting with the lowest energy and then go to higher energy orbitals as needed. And that's where this chart came from. Low energy and then it goes to higher energy. Why do we need to do electron configurations? This is the big long 1s2, 2s2, 2p6 that we did. Those are called electron configurations. What? No, not right now. I need to finish this. Because we use electrons in bonding. And we did that today also. We bonded them together. Okay. Noble gases. The noble gases are the column from helium down to radon. Helium down to radon are your noble gases. Speaking of radon, we don't have it at this house, but we had it at our old house. And Leah, you could ask your Grandpa Bill about this because he did our radon testing at our old house. We had a radon mitigation system, which was like a big tube that went up the back of the house. So that, you can see if you have radon mitigation systems. Well, that's an interesting. It's because Nebraska, I never heard of it till we moved to Nebraska, but there's something about the radon in the soil, I think. I'll have to look into that. That just made me think of it when I said radon. But those are your noble gases. Helium down to radon are your noble gases. So, noble gases are gases at room temperature, and they rarely participate in chemical reactions. That is because they have 8 valence electrons. You wrote on here, in one color, you wrote valence electrons, and above this column, you wrote 8. Remember what I said. You either want 8 or 0, because if you have 0, that means you go down to the next level. To be happy. 8 is your happy number. Okay? So, noble gases have 8. They are happy with their 8. They don't need to bond with other things because they're happy with what they are. Valence electrons are your atom's outermost electrons. So if we had something like, let's do fluorine. Fluorine has 9 electrons. And if we do a Bohr model, just because it's easy to do, 1, 2. We have 2 there. 1, and then we need to get up to 9 electrons. And we can fit, can it be 8 in this shell? Yeah. 1, 2, 3, 4, 5, oh, hold on. 6, 7. So we have our 2, and then we have our 7. Hold on. Elijah! I am trying to do something. Please stop. But our valence electrons are the ones that are going to be in our outermost shell. So if you look at fluorine, you can tell you have a 7 above it to list its valence electrons. It has 7 electrons in its outermost shell, which is why I shouldn't have erased that. We have 2 here, and then in this one you would have 1, 2, 3, 4, 5, 6, 7 to make your total of 9 electrons. Okay? Whatever it has in its outermost shell is its valence electrons. Your valence electrons are where you do bonding. You bond with those valence electrons. That is why we labeled our periodic table with valence electrons. Valence electrons are the ones that bond with other elements. Elements in the same column have similar properties. Remember, you did the little Mendeleev where you were trying to figure out how did he organize these. You guys, I think all of you did mass, and then you put them in columns based on whether they're liquid, solid, or gas. So, elements in the same column have similar properties. Okay, we labeled our valence electrons one color, we labeled our charge another color. To draw your Lewis structures is only going to show your valence electrons. So, we're going to do another one. We did a couple in class. Let's do right now, we will do calcium. Calcium is Ca. Remember, this chart has the words on there. You can also use your textbook if you need to. Calcium has 2 valence electrons. We start at the top You don't really have to. It just makes it simple. And you could go 1, 2. That's it. That is your Lewis structure for calcium. If you wanted to do a Lewis structure for arsenic is As. And it has 1, 2, 3, 4, 5 valence electrons. 1, 2, 3, 4, 5. Now we have 5 valence electrons. Okay. Ion. An ion is an atom that has electrical charge by gaining or losing electrons. If you gain electrons, you're going to have a negative charge because you're gaining negativity. If you lose electrons, you will have a positive charge. An anion is a negative charge. A cation is a positive charge. So ions gain or lose, have electrical charge because they've gained or lost electrons. They do that because they're bonding with something. So, our metals versus non-metals chart. We also colored in metals on your periodic table. The one in the front of the book also has it. If you want to, on this new one I gave you that we labeled valence, you could color in metals and non-metals. Do it based on what's in your textbook. That might be the easiest if you want to do that. A metal loses electrons. Metals have luster. They're malleable, which means you can make them into a sheet. So if you think that you can have metallic sheets. They conduct electricity and they conduct heat. Non-metals gain electrons. They do not have luster. They are brittle, which means they'll break easily. They do not conduct electricity and they do not conduct heat. Ionic compound, which is what we're starting with as ionic, is a metal plus a non-metal. So we did sodium sulfide in class. Let's try another one. Let's do beryllium and oxygen. So beryllium, we look at its charge. So when you're doing this, write each symbol. I wrote each symbol. Write the charge from the periodic table. Beryllium has a +2 charge. Oxygen has a -2 charge. Then we make the charges switch places. Beryllium 2, oxygen 2. If these two numbers are the same, you don't have to have them. We didn't really talk about that, but you don't need them. Okay? Beryllium, and then we name it. To name it, you write the metal, which is beryllium, which I don't know if I can spell right off the top of my head. Beryllium. Then you write the non-metal and you do IDE. We did a ton of these in class, so hopefully you are pretty good with that. There are some non-rule followers. Some things that can gain or lose more or less than 1 electron. For instance, and these are often the ones that are in the middle here. These middle ones, I told you we weren't going to list their valence electrons because they aren't really good rule followers. They don't like rules. So some metals can have more than 1 charge. For example, copper. Copper is Cu and chloride is Cl. Chloride, we know from the periodic table, is -1. Copper can be +1 or +2. And you'll see in your notes, it says copper, and then it has the Roman numeral 1 in parentheses. That tells us that its charge is +1. If it had the 2 in parentheses, then it would be +2. And again, you would just switch this. You would have Cu1, you don't have to write the 1, Cl2. And it's copper chloride. That 2 means we need to write the 2 in parentheses so we know which charge it has. It's a little tricky when you're going from this to writing the name because you have to look here to see what charge copper had. Kind of go backwards to see what charge copper had. So we have the example in your notes of Fe, which is iron, Cl2. So we know it's iron, so we can say iron, but then we need to know what iron's charge is. We look here. This number came from the charge of iron. So that means iron had a charge of 2 chloride. You just work a little backwards on that. Electrolysis, and we'll get to do some electrolysis next week in lab, is breaking down chemical using electricity. Ionic compounds split into ions when dissolved, and those ions move freely in the solution, which is what allows them to conduct electricity. And so we will compare ionic compounds and covalent compounds in the chapter 5. I think chapter 5 talks about covalent compounds. And then we'll see the difference between ionic and covalent. But ionic compounds can conduct electricity because they have all these ions with positive and negative charges just floating around. They don't stay connected. The iron chloride doesn't stay as iron chloride. When you put it in a solution, you get iron floating around and chlorine floating around. They don't necessarily stay hooked together. Okay, so ionic compounds split into ions when dissolved. Those ions just move around the solution. Electrolytes. You've probably had an electrolyte drink if you've drank Gatorade or Powerade. They're chemicals that form a conductive solution when dissolved. Makes me wonder if we could... I think there's a lab on doing that with Gatorade. I'll have to look. Maybe we'll add that to next week. Or 2 weeks. 2 weeks. We don't have chemistry next week. Okay. Electrolytes are chemicals that form a conductive solution when dissolved. Okay. If you have questions, please let me know. We did a lot of this in class, so hopefully this isn't too confusing. And we're figuring this out. And then we will do the labs on chapter 4 in 2 weeks and talk about that. Okay.